Good morning. Welcome to the 10th lecture on this series of lectures on the topic, or rather the course on applied electromagnetics. Today we are going to learn about the gradient theorem or theorem of gradients. Okay, having learned the derivatives that have been obtained by the operation of del operator on a scalar function yielding the gradient of the scalar function, which is the resultant quantity, the gradient is a vector, and the divergence of a vector function resulting in a scalar quantity and curl of a vector function resulting in a vector quantity. So having learned those fundamentals, we are going to learn the corresponding three theorems in the next three classes. The first one is the gradient theorem, which we are going to see today. So the first, before we go into the gradient theorem, let us look at the fundamental theorem of calculus. What does this theorem tell us? Okay. So if you look at the fundamental theorem of calculus, it actually, let us take for example, a rectangular coordinate system, and let us say this is my function, and I want to evaluate this function between these 2 points. Okay, so these are the 2 points that you are seeing. Point A, how much this function f of x, because it is only a function of one variable, change, how much the function changes when we move from point A to point B. This is the question that we need to answer. So the answer lies in the fundamental theorem of calculus. So there are 2 ways of doing to know the change. When I move from point A to point B, how much the change? There are 2 ways of doing it. Okay, so the first one is obviously you can actually see that moment I know what is the value over here of the function and what is the value over here of this function, the theorem tells us that it is enough to know the values at the end points, point A and point B. Okay, point A and point B, it is enough to know these 2 values. So here you will get point A, point B, and f of A corresponding function value f of A and f of B. So once I have these values, I can actually, to know the difference between the point A and point B, all I need to do is to subtract the values of the function at the end points. So f of B minus f of A. And this being a curve, so you might be wondering how that is correct. Okay, so that is where the theorem has been proved that to do that, actually what is seen is actually if you take this segment between point A and point B and you break these segments into several small linear segments like this. Only a few representative segments are shown, and these segments actually what you need to do is you can actually correspondingly you can note down what is the x coordinate or what is the y coordinate. So y coordinate is the value of the function at that point, and similarly for this point here, similarly at this point here. Okay, I have shown only few ones, but you can actually make the steps to be very small so that the accuracy of the result that you are going to get is going to be spot on depending on the resolution of this point. Okay. Now, so I can, once I know the values of these functions, I can easily see the difference in the values between these 2 points and get the answer and keep adding that. So that is like summation. So know the difference between these 2 points. So that is one way. Secondly, moment I take a linear segment, actually what I can do is I know what is the slope, and from the slope I can find the corresponding y coordinate by applying the difference in the x coordinate. So we can actually, so when I move in the x coordinate some incremental distance, when I move on the x coordinate some incremental distance, say I am at one point, say x, and I move to another point which is x plus dx. So the distance I have moved from this small incremental distance is x plus dx minus x, which is dx. So when I move a distance of dx, the corresponding change in y will be dy. How much will be dy? So knowing the point here, knowing the value here, okay, knowing the value here and knowing the value here, I can subtract the dy, get the dy and keep adding like the dy. So basically, essentially, the theorem can be written in this fashion. So integral of x to x of a to x of b will be df by dx, which is the slope of this function multiplied by the incremental distance dx equal to f of b minus f of a. This is what the theorem is. Okay. So there are two methods of. So probably you might have seen an alternative version. Df by dx will be written as f dash of x, which is nothing but the first order differential. Okay. So first order differential will be f dash of x. Okay. So that is what you must have seen in your textbook. So let us say I have function f equal to x cube. Then f dash of x will be 3x square, or e power x, differential will be e power x. Okay, and correspondingly, depending on the points, I can simply, so it is enough to know the value of the function at the end points rather than breaking our head of chopping this path between point A to point B into several small linear segments. These small linear steps are what is known as the infinitesimal displacement. So I am moving from A to B. Therefore, I have to use the, I use the word displacement. Okay, to be more precise. So two ways of computing. This is what the conclusion is. Let us validate whether how far this is true by a suitable example. So let me take the theorem back again. So f dash of x I have written so that you are familiar with this way of notation. So this is the first order differential f dash of x for the function f of x. And this is a function with one variable. Remember that. So let us say I have function f of x equal to x square. What will be f dash of x? F dash of x will be 2x. dy by dx will be 2x. That is f dash of x. Having said that, so I know that, so let me say I want to move from point 1 to 5 along x direction. Okay, y and z I am not considering because the function is only variable, varies only with respect to one coordinate. Therefore, I am taking only one variable. So I am moving from point 1 to 5. Okay, let us assume that this function is not varying with respect to y and z. I don't have to bother about that y and z. For now, I am going to only stick to one variable. We'll come to that when a function varies with three variables. We'll come to that after we complete this. So f dash of x. So this, the right hand side is super simple because we don't have to break that path into several linear segments. Rather, we can actually straight away substitute what is, we know the f of x. So we can substitute what is f of 5 minus f of 1. So moment I substitute, what do I get? I will get 24 because 2 power this 5 power 2 is 25 minus 1 power 2. Okay, that is 1. So 25 minus 1 is 24. So that is what we are getting. Now what about the left hand side? This is the question we must answer. So as I told you from the figure, remember that figure, I have a segment like this. I am chopping into several intervals. So I can find when I move a distance of dx along x coordinate, how much the function varies in the y coordinate. Similarly, another dx to how much. So like that I can keep. So essentially, this statement is akin to writing this mathematical form in this fashion. So I am going from 1 to 5, that is the difference in the value of the function is the end point minus the source point. So I am going to have f of x equal to 5 minus f of x equal to 1 will be equivalent to. So I am going from, let us say I am going from 1 to 2. So that will be this value, 2 to 3, then 3 to 4, then 4 to 5. Like that I am going. So I have broken this going of from point 1 to point 5. I am going to go in 4 steps. One step, second step, third step, fourth step. So if I know the values of the function at end points, I can easily at these points which are denoted, which means at x equal to 1, x equal to 2, x equal to 3 and x equal to 4 and x equal to 5. If I know the values of the function, I can actually get this. So these are the values which substitution you will get that. Now you add all of these, what will you get? 9 plus 7, 16, 16 plus 8, 24. So are we not getting it? So which means I can actually, it is enough to know the values of the function at the boundaries. The boundaries of a path line is nothing but the end points. So if I know the values of the function at the end points, I can simply subtract the values irrespective of whichever this thing. So I could have taken another path. I could have still reached that point, and then I can also see that it is going to be similar. And similarly, I could have broken these points, okay, into several segments. Similarly, I can do that. Now this is a scalar function. Remember this, and this is a function of one variable. What if the function varies as 3 variables, more than one variable? Then what am I going to do? How will I compute the change in value of the function when moving from one point to another? So the answer to that, obviously, we have already learned the gradient, and we know that we are learning the theorem of gradients. So the answer must lie in determining the gradient of a scalar function and then applying it. How, and you remember gradient is a vector quantity. So how am I going to solve this puzzle? Let us take this Cartesian coordinate system, and I have this function like this, which varies as a function of 3 variables, namely namely x, y, z, and I want to calculate between the change in the function value as I move from point A, which is denoted as x1, y1, z1, to point B, x2, y2, z2. So when I move along this path, I have shown one path. Now we'll come to that. If I take different path, what happens? But first let us answer what will be the change in the value of the function when moving from point A to point B. This is what we need to see. To see that, what I am going to do is very similar to the previous approach. I am going to break. First thing is, you can see because there is a direction of movement is keep changing, and I told you already that the gradient. So here I have to invoke through the by invoking partial derivative, we can actually find the directional derivative through the gradient, and then take the line integral of the gradient. We will get the answer. So that's what we are going to see. So dt is the, let us say, the scalar function that I am dealing with is a temperature function, and the temperature function varies along this path like this, and dt is given by del t dot dl by through the theorem of partial derivatives. We have already learned this, so I have written the expression. So if I expand this expansion further, I will get dt equal to mod del t mod dl cosine of the angle theta between del t and dl vectors. Okay, so what I am going to do is, to understand this theorem, I am going to, similar to the previous approach, I am going to break the segments like this. What I have done is, I have taken very small linear steps like this and gotten the path like that. So I'm at any point of time, what I'm going to do is, I'm going to calculate the del t at this point and dot it with the displacement vector dl. Similarly, I do that del t between this point and this point. At this point, I compute what is del t and dot it with the displacement. At this point, I compute del t, dot it with this thing. So essentially, I will be getting dt will be equal to dt. That will be the change in the temperature function between point B and point A is actually summation of this whatever the variations that we are going to obtain. I can sum it up like I can write, for example, del t1 dot dl1 del T2 dot dl2 del T. So I take dot products. When both are along the same direction, we are going to get actually the same angle is 0, which means we are going to get simply the mod del T dl. So I can keep multiplying it and then summing it up together, and I can reach the point B. Alternatively, it is enough to know, this theorem states, it is enough to know the value of the function at the end points at the boundary, that is point B and point A. So the mathematical form of the statement is of the gradient theorem is nothing but when moving from point A to point B, the summation is replaced by integration when you are taking several linear infinitesimal steps, which means I want to do this way. The easiest way will be to invoke integration and get this done easily in one shot. Okay, so that is the way it is written, and we know that the dot product between del T and dl is going to be a scalar quantity. So resulting in we will get when I take the line integral of the gradient, we are going to get the temperature function, and corresponding to the substitute these points, we will get TB minus TA. Now, how far this is true, we will again go through an example to understand this. Indeed, that is correct. Okay. That is, this is what you must remember. Okay. Instead of elaborate mathematical proof, I have just given the way it is to be done. Now, if you, let us say, I am climbing Eiffel Tower, or I am climbing, going to my first floor from ground floor, I have a ladder, okay, and the ladder, if you see, I have to take several steps to reach the first floor. There will be, say, let us say 20 steps. So at each step, actually, I am moving by displacement by along certain direction. In this case, it will be z direction. So I know the displacement vector, and I also know what will be the gradient. So if the steps are not linear, if it is linear, I know that the direction will be the steepest ascent of the gradient, and the dl also points in the same direction, which means I can take the dot correspondingly at each step. I can keep adding del t dot dl and sum it up, and you will see that the height is going to be the same as the if I know the height of at the end point where it is located and the location, I know what is the distance between these, so I can actually calculate what is the height. So alternatively, I can take the incremental steps and get there. So this is the sum and substance of this gradient theorem. Okay, so either you chop it into very small intervals, take the gradient at each small interval, dot it with the displacement vector, or you can actually know the values of the function at the end points just to subtract it. So it is strikingly similar to what we saw with fundamental theorem of calculus. Okay, so that is the thing. Now this is known as the fundamental theorem of gradient. So same thing with the Eiffel Tower. So if I know the gradient at each step, small infinitesimal step, take the displacement, rather the height at each step I am taking, sum it up, that will be the same as putting an altimeter at the top of the Eiffel Tower and at the ground, get the values with the altimeter, just to subtract the values. So both are same. Okay, so that is the statement of gradient theorem. Now the question is the gradient theorem path independent? Okay, that is what we need to tell. Okay, is it valid if I take different paths? Is the theorem valid? Okay, so obviously, because the right hand side tells you that it is T of B minus T of A, which means only the end points matter, not the path in which. So obviously the answer has to be yes. Okay, so that is, so this is my So the question is, this is the question, and is it path independent? So to answer that, we are going to give that answer. Yes, indeed it is path independent. So no matter whether I take this path or this path, okay, in either case I am going to get, okay, the answer will be the same. So line integral of the gradient, okay, I say line integral because we are dotting with the displacement vector. Line integral of the gradient, and we use the dot because both are vectors. Line integral of the gradient is given by the value of the function at the boundaries. Okay, it is now having, so these are the two corollaries. Because it is dependent only on endpoints by this thing, obviously the first corollary for that will be it is path independent. Secondly, if I go along one particular path and return, I can go along this path and return along this path. I can go along this path and return along this path. I can retrace the path. Either way, when I am going around the circle, okay, it's a closed line integral. This circle on the integral means we are returning to the same original position. That is the indication of the circle. So once you have a closed line integral, obviously the right hand side will become of this equation, gradient theorem will become T of A minus T of A, which will be 0. Obviously, closed line integral of del T dot dl should be 0. Okay, so these are two corollaries. Okay, what is the contextual sense to electrostatics is very important. In electrostatics, we are going to deal with a function, namely scalar function, namely the electric potential. Okay, and we will come to the, and we are also going to deal with vector function E, which is the electric field. Okay, which means the whose value will be different at different points, pointing in different direction. That's a vector function. That is electric field. But scalar value at any point in space, it will be associated only with value. So this, I take the gradient of this potential function, and I will see that the gradient of the potential function is equivalent to the electric field. Only thing is, we will have to get a negative sign, which means E, which represents the electric field, capital E, will be equal to minus del V. The minus sign comes from the fact that with respect to reference point, which is normally taken as infinity, we have to do work to put a charge in space. Therefore, that minus sign will be coming, which I will explain later. Okay, at the time of explaining the concept of electrostatic potential. Okay, so V and E are related. A scalar function is related to a vector function through taking the gradient of the scalar function and the negative sign, with the negative sign, E equal to minus del V. And not only that, so from this equation, because T is a scalar function, so is V vector, so is V electrostatic potential. So del V is going to be E dot dl, because V E is nothing but del V. Okay, just follow with me. Do not get afraid. We will deal with that after I deal the electrostatic field and potential. I will again come back. But whenever you learn mathematics, for this course on applied electromagnetics, it is essential for me to bring the context. Why we are learning this particular theorem. That is my purpose, without which this class is incomplete. Therefore, I am actually trying to explain the context, why I am bringing the gradient theorem. So we will prove that E equal to minus del V. So here I can substitute E dot dl. So obviously E dot dl has to be path independent, and also E dot dl around a closed loop must be 0. Okay, these are the two corollaries. Okay, so this we will prove it at the time of dealing with electrostatic field and electrostatic potential. So whenever you have a scalar function, you can take gradient. Gradient can always be taken only on a scalar function. So let us take one example and evaluate on the left hand side of this gradient theorem and the right hand side of the gradient theorem and prove that indeed that is also correct. So my function is going to be xy square. I am moving from point A to B, and point A to B is like point A is given as 0, 0, 0. Point B is given as 2, 1, 0. So I am going to move from point A to point B. How am I going to do this? Okay, that is the question. So let us rewrite the statement of the gradient theorem as this, and you can see that moment I have this, you can easily see the z coordinate is unchanged, so I can convert this problem into a two-dimensional problem and get this value. To get that two-dimensional problem, what I'm going to, so I'm changing my movement is changing in both x and y, not in z. So therefore it is a two-dimensional problem. So the easiest way obviously is going to be the right hand side. So let us evaluate the right hand side. The right hand side is going to be T of B minus T of A equal to 2 into 1 square, because y is actually changing from 0 to 1. So xy square means 2 into 1 square, and here it is all 0, 0. That is, I am moving from origin to this point. Now the right hand side is what we have to worry about. The right hand side. How am I going to worry about the right hand side? To worry about the right hand side, what I am going to do is I have to choose path. Okay. So what is the to evaluate the right hand side we have the answer. To evaluate the left hand side we need to do it. So left hand side, how am I going to evaluate? That is the question. To evaluate left hand side, what I am going to do is I need to go from point. I can directly go to this point. That is one option. Alternatively, I can move along x direction to begin with and then move along y direction to reach that point. Okay, from 0 to 2, 0 to 1. So I can visualize this problem in this manner. So first let us evaluate del t. So I have evaluated del t, which is the gradient, and visualization requires actually which path I must choose. That is the thing. So visualization can be seen through this diagram illustration. So first I move along the x-axis and then I move along the y-axis. So this is one way of moving. Alternatively, I could have moved along y-axis and then x-axis. Or alternatively, the third way will be directly moving. Or any other way I can move to this point, no issues. Okay, because it is path independent. See, the vector function for which the line integral is path independent. Okay, line integral of a vector function, if it is path independent, in such a case we can say it represents a conservative vector function. Okay, so for example, we will talk about electrostatic field. We will see that electrostatic field is a conservative field. Okay, we will again come on that. So here I could have done this path, I could have done this path, I could have done this path, I could have done this path. All the three paths I could have chosen, but I am going to choose this path and move along this direction. So when moving from along this path, so I refer that path to be path 1. When moving from this path, I refer, which means this path, from this point here to point B. I will denote that point to be 0, C, and that point is going to be C is going to be, let me tell you. So this point C is going to be 2, 0, because Y there is no movement. The movement is only along x-axis. So it is 2, 0, 2, 2, 1. I am moving. So this is the end point I want to move. I could have done this way, I could have done this way. For a problem, when you attack a problem, you have to choose some specific path. It doesn't matter which path you choose. I have chosen this path. And I will also show that this is path independent. That will be my third part of the problem. So that will be path 3. Okay. So I am moving along AC. So C is represented there. So when I move along AC, actually I am moving only along x direction. Therefore, my dl reduces to dx x hat, because there is no movement along y-axis. Dy is essentially 0 and y coordinate is 0. That is what is written here. Dy is also 0, which means the only variable is x. So when I take this del t dot for the with the given function del t dot dx x hat. This term is not there because dy is 0. Only x hat dot x hat is 1, whereas x hat dot y hat, anyway this is 0, so we don't have to even bother about it. What about this one? Y hat dot x hat will be 0 because these are orthogonal coordinates. Therefore, dot product between orthogonal coordinate axis is 0. So essentially there is only one term, y square dx. Integral of y square dx, that is going to be along the path 1, and y is 0, therefore this integral vanishes. So the value of this left hand side when I am moving along x direction, that is going to be 0. Now to reach this point I have to evaluate one integral first, then I integrate. So it is called like integration by segments. So first integration, second integration, then add it up. That's what I'm going to do. Now I'm going to construct for path 2. So path 2 is from C to B. Okay, path 2 is from C to B, not C to A, C to B. So path integration is from C to B. When I'm moving along C to B, I am going to get the values same manner. Now only I got to again write the expression for the del t first to recall from the previous slide, and then I get the dl. Now here dl will become only along y moment, therefore dx is 0. So I write dl as dy, simply dy y hat. dy y hat. dy y hat. And y moves from 0 to 1, x equal to stationary point, x equal to 2. Okay, so once I do the del t dot dl, I am going to get this. These are perpendicular, this x hat and y hat are perpendicular, so this term is going to vanish. This term is going to lead to line integration of 2xy dy from moving from point 0 to 1. So that is written like this. And you will get essentially, once I have that 2xy and substitute for x equal to 2, you will get 4y dy, and then I will get 2, and that is the value. So along this path the line integral is 2, along this path line integral is 0. What will be the total sum of it? Net sum will be 0 plus 2, that will be 2. That is about the left hand side. That is about the left hand side. There are some typos I have corrected. So that is about the left hand side. So once I have the left hand side, and what was the value at the right hand side? We have seen in the previous one. This is the thing. So I have seen this. So the right hand side gives 2. Left hand side we just evaluated on point path 1 and path 2 and found out that we are going to get actually we are going to get what? We are going to get 2. So right hand side equal to left hand side. So we have proved validated the theorem of gradients. Now the corollary we will validate by moving directly from point A to point B. In this case, along this path, actually you can see that and you can see here along this path it is going to vary in both x direction and y direction at any point. So which means my dl will be simply dx x hat plus dy y hat. Now I have to bring both the variation along the x and y coordinate. Therefore, my infinitesimal displacement vector also will be varying with x and y. So I must write dx x hat. So previously along the paths along the respective axis, there is only one coordinate varying, but along directly reaching that point, you have to bring in. If it is a three-dimensional system, I have to still bring dx x hat plus dy y hat plus dz z hat. For example, if I am moving from 0, 0, 1 to 2, 1, 1, 2, 1, 2, let us say, or 2, 1, 5. So all the three coordinates are varying. Then in which case I must write dl equal to vector dl will be equivalent to dx x hat plus dy y hat. plus dc z dot. Okay, so I have to do such a problems. The more we learn to do how to do these problems, which you must have learned in vector calculus. This is only a refresher course that you are learning, but this refresher course is very much essential for understanding, for making the electromagnetics to be understood, to facilitate the understanding of electromagnetics in a much smoother manner. Okay, so that is the main thing. Okay, so mathematics, we are going to take the help of mathematics only to learn electromagnetics. We are not learning mathematics for the sake of learning mathematics. That is the fundamental difference between this course and the previous course which you did in mathematics department. Okay, so once I finish in another 5 classes complete mathematics, we are going to directly jump to electrostatics, and I will not repeat whatever mathematics steps which I am repeating now over there. I'll simply write the answer. You must actually apply these mathematical principles to get there. Okay, so this is the essence of these lessons. So once I substitute along these 3 paths, what is the technique? Now, when 2 variables are varying, what is the technique? When 2 variables are varying, the technique will be, because now I see that del t has both variables. I cannot take it out of the line integral. Okay, I cannot take it out of the line integral. So I must find a way out. So the way out will be to actually find a relationship between these variables, so that I can bring everything, the equation, entire equation into one single variable. Then it is easy to handle. This is the nuance or the method. Okay, the subtle information that I want to present through this problem. The way of attacking this problem is to determine the relationship between x and y, and then once I have a relationship between x and y, I can find what is dx in terms of dy, and wherever I find, I can either replace in the equation all y's, or I can replace all x. Okay, so this is how, and then get in one variable, and then the solution is straightforward. So equation of the line here, the line is going to be passing, the equation of the line when moving from point A to point B will be y equal to mx, where m is the slope of this equation and m is given by y2 minus y1 by x2 minus x1. So y2 minus y1 will be 1 comma 1 minus 0 divided by 2 minus 0 x2 minus x1. So what will be the slope of this equation? Slope will be equivalent to m will be 2, m will be 1 by 2, and therefore the equation will be y equal to half x. So dy will be essentially equivalent to half of dx. So what does that mean? What it means is, when I move 2 steps along x direction, my y is going to vary by only 1 unit. That is the meaning of this equation. When I am moving 2 steps in x, my y will vary only by 1 step. So dy will be half dx. So I substitute everything over here on that line integral, and I am going to get and evaluate. So what I have done here, so I have taken the first the dot product, and the dot product, once I substitute, and here y is there. Here in this, the way I have attacked is, actually I have substituted all y's in terms of x and also dy in terms of dx. So once I do that, I am going to get 3x square by 4 dx. The limits of the integral obviously has to be x variable, which is between 0 to 2. So once I do that, I am going to get 3 x cube by 4 into 3. The 3 will get cancelled, and x cube by 4, x equal to 2. So x cube will be 8, 2 power 3 divided by 4. So which means 8 by 4, that will be answer will be 2. So did we not get the answer path 1 and path 2? So this answer is not surprising. What have we done? We have done through this problem, we have proved the validity for the gradient theorem. Also, we have understood the conservative nature of a gradient of a scalar function. Okay, so we have seen that by proving the line integral of the derivative, in this case gradient is path independent. Okay, so the final statement of this class is the definition of gradient theorem in text. So this is the statement of the theorem. The theorem tells us that the line integral of a derivative within bracket gradient is given by the value of the function at the boundaries and here end points. Okay, thank you.